Let's look at a rather famous engineering problem. I think every Calculus 1 student has seen this problem in some form or fashion. It's a tried and true problem in the calculus sequence. And this is for optimization. So what we're trying to do is maximize the volume of a right circular cone that can be inscribed in a sphere of given radius r. And we're asked to actually determine its radius. That is, if we maximize the volume of the cone, what is its actual radius relative to the sphere? And over here I've written in red, r is fixed. It's a positive number and it's fixed. So by being fixed, it is constant. Now, this problem can be done by thinking of a great circle. That is, we inscribe the right circular cone and then we cut right through the center of the sphere to form a great circle. And this cross section gives us the geometry that we need to do this problem. Once you have this, the problem is very simple. So if you take the center of the sphere, you can actually write in the vertices of the right circular cone relative to the sphere running through the center. And as you do that, you see that you get copies of the radius of the sphere. You have a copy of r here, you have a copy of r here. And to make this problem work, we're actually going to take x to be a variable that lives between 0 and r. So when we look at this particular problem, we're thinking of the height of the cone being the radius of the sphere plus this variable x. And we really need to figure out what x is. The idea here is that if x happens to be negative, the calculus will tell us that. But at least intuitively looks that x would have to be greater than 0 and less than r. And of course, this is a closed bounded set, so we will have to check endpoints. Now, in order to make the problem run through a little bit better, we will designate the radius of the right circular cone to be an uppercase R. So what I've written here is let R be the radius of the cone. Now, nicely enough, I've noted the right triangle that we have here, and so by the Pythagorean theorem, x squared plus uppercase r squared is lowercase r squared, the Pythagorean theorem. And then, of course, we can easily solve for r squared. We get lowercase r squared minus x squared. I might just start saying little r. And now, of course, in a Calculus 1 problem, you will use a fact from geometry that, of course, we won't be able to rigorously prove until we get to Calculus 2, but we're going to define V, the volume of the right circular cone, as a function of x. So we know that's actually the square of the radius of the cone times its height. So if you look over here, the way we've set up this great circle, the height of the cone will just be the radius of the sphere plus the variable x, or x plus r. And so here for the height, we have x plus r. And then the only other thing we need to do is to rewrite r squared in terms of this function here in the blue box, little r squared minus x squared. And so now we have a function of x, which represents the volume of the right circular cone that's inscribed in the sphere. And so over here I've written we'll use the extreme value theorem because that will tell us we need to check endpoints, and we'll use Fermat because we know if a function has a relative extremum, it must occur at a critical number. So the first thing we need to do, over here you see I have a tabulation, but we need to go ahead and compute the derivative. And what I've done here is I've left this in the factored form, and I want to use the product rule. I think as I work through this, it turned out to be a lot easier. So now we factor the pi over 3. We differentiate the first factor. We get a negative 2x. Remember, the r is constant. And then in the second term, we leave this one alone, but we differentiate with respect to x here and just get a 1. So we're only left with r squared minus x squared. Now, the algebra turns out to be really nice. This is just a difference of two squares, which we write here. And now notice that we have a common factor. We have an x plus r here, and we have an x plus r here. And so in doing that, we factor, and we're left behind with a negative 2x and an r minus x. of course, that's going to give us negative 3 copies of x and 1 copy of r. So I'm going to go ahead and factor the negative 3 here. And so that'll leave us with a negative 3 pi divided by 3. We have the x plus r, and left out here, we'll have an x minus an r over 3. That is when we factor the negative 3, the x is as it is, but of course we have to compensate here because r is just r here. So we need to have negative r divided by 3 to make this equivalent to the previous expression. And so now, if you like, what we can see here is we've got a nice factored form. We can use the zero product law. So this is always defined, but it can be zero. So again, we look for the definition of critical number. So we set this to 0. So what we see is that x could be the additive inverse of r, or x could be r over 3. Of course, the additive inverse of r makes x negative, and we're not really very interested in that, because if x is negative r, then the height is 0, and so we don't have any cone. So we're going to discard that right away. That's not going to give us anything that's useful. But this value here for x, r over 3, which lives between 0 and r, is actually something of interest to us. So again, we're going to use EBT and Fermat. So EBT says check the endpoints, and Fermat says check the critical numbers. So again, we have our formula for the volume of the right circular cone. And when we substitute 0, notice here, we just have an r squared left and an r, and we just get 3 copies of r times pi over 3. And for convenience here, I just wrote this with the denominator of 81, so that would give us a 27 upstairs. Now when we try r over 3, again here, r over 3, that's just going to be r squared over 9. And when we subtract from r squared, that's going to give us 8/9 copies of r squared. And then, of course, here r over 3 plus r will give us 4/3 r. When we multiply this out, notice we've got, 81 downstairs and a 32 here. Now, you can see why I did the common denominator there. But just lastly, we'll also notice if x is equal to r, then the factor here will zero out the volume. So we get a volume of 0, which of course is not of any interest to us. But now, as you see with the common denominator here, this is the larger number. So by checking endpoints and Fermat, or interior points, we actually have the largest volume, which occurs when x is equal to r over 3, which I've noted right here in red. Now the problem says determine its radius, that is the radius of the right circular cone. So we go right back to this formula. We take the principal square root of this, that is, and now replace x with what? R over 3, and we've done this computation before. Now we have the principal square root of 8/9 r squared, and then of course that'll just be 2 root 2 divided by 3 times r, the square root of r squared being the absolute value of r, but r is positive, so we have this. So we actually know the maximum volume of the right circular cone, and now we actually know its actual radius. And we are done.